Aloha nui kako. Hello, everyone. Welcome to Live from NOIRLab at Hawaii. My name is Leilani Lozi, and I am an outreach assistant at Gemini Observatory, a program of NSF's NOIRLab in Hilo, Hawaii. And today I have a couple people joining us for our presentation. In the Zoom room with me is Jamaica Marshall, also an outreach assistant here with me at Gemini Observatory. And we have our special guest, Michael Warner, who is a senior electronic engineer from the Cerro Tololo Inter-American Observatory in Chile. Now, a little bit about Michael before we dive into our intro about Gemini Observatory. Michael Warner arrived at CTIO in the year 2000 as senior electronics engineer. He has worked on large projects such as the development of the ISPI instrument, the integration of SOAR, the Blanco telescope TCS upgrade in preparation for DECCAM, and the design of the Vera C. Rubin Observatory subsystems, among other many tasks. He had previously worked in Tucson at Kitt Peak National Observatory from 1974 to 1978, and in the Raytheon Engineering Company from 1978 to 2000. In 2002, shortly after returning to Chile, Michael met Rodrigo Martinez, a leading Chilean meteorite hunter. Michael's passion for learning more about the formation of the solar system and the information that meteorites can deliver led him to accompanying his friend in the search for these impressive objects, and to begin what would hopefully become his own hobby, finding meteorites. So mahalo to Michael for joining us today. I know he has a wonderful presentation prepared for all of us, and then a special treat at the end of the presentation. Our Live from NOIRLab is a little different today. If you have any questions or comments, please leave them in the YouTube chat, and we will answer all of your questions at the end of the presentation. Okay, now a little bit about Gemini, which if you frequently tune into our show, you know a lot of this by now, but Gemini Observatory is, of course, a twin telescope consisting of Gemini North on Mauna Kea, Hawaii, and Gemini South on Cerro Pachon in Chile. Gemini is funded by international participants, including the United States, Canada, Chile, Brazil, Argentina, and Korea. In our most recent science news, we have a pretty interesting CosmoView video for you here from a press release titled, "Are We Missing Other Earths?" So this link here we will add to the YouTube description when this video is uploaded a bit later. All right, that was a great song for that video. Okay, and a little update from our home of Hawaii here. We are so happy to be back out in the community doing outreach after, of course, the COVID-19 pandemic kept most of us at home for a while. We are safely getting back out there, all masked up, and reaching our local students again with activities through the Summer Fun program, which we partner with the Hawaii County Parks and Recreation Department on. And we also had the pleasure of being a part of the Pisces summer STEM camp for girls. And those are really great programs. We do have, this is a sneak peek for all of you who are tuning in today. We have an exciting new event coming next week here in Hilo, Hawaii. On July 7th, we'll be doing the first ever Hilo Solar System Walk, inspired by the Waimea Solar System Walk, which took place just in the fall last year, where it'll be a hybrid event of informational videos in English and Olelo Hawaii, the Hawaiian language. And you can just walk around the park and find the different signs for the different planets spaced accordingly to how they would be in the solar system. So we're very much looking forward to being a part of that and hopefully seeing you get some exercise out in the park. And with that, we can start our show on asteroids, meteorites, and chondrites with Michael Warner. Go ahead, Michael.
Thank you for the pretty great introduction. It's a pleasure and an honor to participate in the International Meteorite Day, and I will start my presentation. Okay, basically today's talk is going to be to celebrate the International Meteorite Day, June 30th, and we did this presentation last year in Spanish, and this year I've been honored to do it directly from Hawaii in English. And the talk is going to be relating asteroids, meteorites, and chondrites, which are really I would explain later on what they really are. It's the most important part of the meteorite collection, because they can tell us a story about how the solar system was actually formed. Go next slide. Okay, the agenda for today is going to be basically we're going to talk about the origin and the formation of the solar system, asteroids, and the relationship with them and the meteorites. And basically we go show how the meteorites are classified, how to recognize them, where to find them, and also I will go into my experience with the Chilean meteorite search, and I would show some of the important sites in Chile. One of them is the Monturaqui Crater, which is a source of impactite, the Imilac, which is a type of very rare type of Pallasites, and Vaca Muerta is a Mesosiderite, and also I will show some of my experience searching for meteorites in the desert. And already I have 61 meteorites scientifically classified in my name. And also would show some very important discovery we did a few years ago, finding the new Atacama tektites. This is a very simple chart, shows the formation of the solar system. This starts from a nebula, which has some kind of rotation, and then eventually formed this really large disk, which kind of segregated down to the bigger planets. And then eventually you get the whole solar system made after a few million years. And this is it's a diagram showing some of the theories how the solar system was made. You start from the nebula, which has a gravitational collapse, and then you have the left side, which goes to the basically a proto-sun, and then from heating and gravity, you start the nuclear. The sun fusion starts, and then from the right side you get the proton from the disk. It goes through the condensing phase, and then you get the rocks and metal, which eventually made what are called the terrestrial planets, and also the gases and ice through accretion. They make the Hawaiian planets, which are Jupiter, Saturn, Neptune, and Uranus. And some of the leftover materials in the gas and ice phase makes the comets, and the leftovers from the accretion phase of the metal and rocks made the asteroids. And that's where the source of the asteroids came, at least one of the theories where they came from. And some of the processes just show some diagrams on the process of the formation. You get this nebula, which eventually start, since a lot of impacts between each other, and then basically eventually you end up with this kind of view of the solar system right now, the inner solar system from Jupiter. And you get all the asteroids, which are really about over 1 million asteroids have been discovered today, and some of them, very few, cross the Earth's orbit, and those are the sources of the meteorites. So they are really asteroids that came in the same neighborhood of the Earth. And this shows a video of the inner solar system. And you can see this, the Earth's orbit. And from the million asteroids, there are only about 22,000 near-Earth asteroids they've been discovered. And probably many, many more will be discovered in the future because they pose a threat to Earth. And some small pieces of them fall down on Earth. And mostly all the meteorites originate in the main asteroid belt between Mars and Jupiter, which slowly drifts and become the NEAs, and also a very small number of meteorites originate from the Mars and the Moon. Basically, a larger impact in the Moon can spray Moon material and then eventually falls down to Earth, and also in Mars. And right now there are about 66,000 meteorites have been classified, and mostly all of them have been found in the hot deserts in Africa and in Antarctica, and right now in Chile. And depending on how the meteorites are discovered, they can fall in two groups: the finds, where basically they've been laying in the ground for many, many years and somebody finds them, or witness falls. The most interesting one, because basically people can see them falling down, and they can do some serious damage sometimes, like in the next chart. One of these very famous fall in the US, Peekskill, New York. In 1992, there was roughly a 12-kilogram meteorite that fell down, and the image in the right, on the left, basically was taken during a football game, and people took the video of the meteorite falling down, and eventually the meteorite hit a red Malibu, and this car actually was sold in the Tucson Mineral Gem Show for $50,000 because it was actually had some kind of value for being hit by a type H6 chondrite. I will explain in a little while what the chondrites mean. There's another one that fell down in Russia in 1913. That was roughly a 20-meter high-speed super bolide, which was hit the atmosphere about 65,000 kilometers per hour, and it had the energy of about 25 Hiroshima bombs. And it luckily exploded very high in the atmosphere, and it did not cause major damage down in the ground, and except that there was about 7,000 buildings damaged, about 1,500 people hurt, mostly from flying glass. And there was in a lake, they found the largest mass, about 644 kilos. And they happen to be another type of a very common type of meteorite, well, called the chondrites. This shows some of the diagrams showing some of the two types of meteorites. One they call the non-differentiated, which really the most primitive ones, which are made from basically the Carbonaceous, or what I call the ordinary chondrite, which is, I don't see anything ordinary about them, but that's the name they're called. And depending on where they originate, either from the planetesimal, which has been made, and some of the types 3, 4, 5, 6, it depends on the amount of thermal heating. So you can see that some of the type 6 might be in the inner core of a planet that tried to form, or asteroid that tried to form. And the type 3 might be in the outside, in the crust. And then differentiated are basically they are much bigger asteroids, which actually made, they might have basically a solid, well not solid, but iron mantle or core. And this basically causes the core will generate the iron meteorites, and then the crust will generate what they call the Chondrites. And also there are some other meteorites by originating Mars and the Moon, and they eventually fall down to Earth. This is a very simple view of the classification scheme. All meteorites can be, as I explained before, they can be non-differentiated or differentiated. And the non-differentiated can be either stony, and the differentiated can be stony iron, or iron meteorites. And then the stony iron will give rise to what they call the ordinary chondrites, which can be L, or H, which indicates the amount of metal, either low, very low metal, or high metal. Well, the metal is actually just iron and nickel, which is the only metals that you find in meteorites. And then this whole selection of carbonaceous chondrites, which there are about 9 different types of them. And the differentiator can be, the stony can be what I call the achondrite. There's something called the HED clan, which is most likely from the asteroid Vesta. The SMC clan, which actually originates from Mars, and then the lunars and many others, achondrites, which I don't want to go in too much detail. And the stony iron can be divided in Pallasites and Mesosiderites. And then the iron meteorite can be hexadrites, octadrite, and ataxites. This is a very general classification. Stony, mainly made from silicon minerals, and also has some small amount of iron and nickel, which form 97% of the meteorites found. The stony iron, which are containing metallic and rocky material, which are 0.6%. And then the iron, which is most likely composed of iron nickel, 2.3% of the meteorites found. The stony meteorite can be further divided in chondrites, which is 92%, and they contain small round particles called chondrules, which are mainly silicas that formed about 4,565 million years ago during the birth of the solar system. And to me, those are the most important pieces of information, is because they actually contain the information of the actual birth of our solar system. And these are embedded in this very common type of meteorites, which came from the asteroids. And then the chondrites are mostly rocky material, which originates from Vesta, the HED clan, and a group from Mars, the Moon, and several others like Uralites, Instantites, Angrites, Acapulcoites, Brachinites. And right now they don't have a good idea of where those came from. They haven't pinned down the source of them, so they're very interesting. Yeah, stony. These are just shows a couple of pictures of the stony meteorites with their chondrites, which are, you can see the picture on the left is a typical chondrite from the outside, but if you cut them, you will see these many little spheres, which are the chondrules. And that's the clue there. That's the way the information, the ordinary chondrites contain these chondrules, and each one of them is like a little microplanet that was just joined together and formed these meteorites. And then the chondrites are just they're much more evolved. They're not so primitive as the chondrite. And this particular one is a lunar chondrite. And it shows a little bit of how the chondrites were originated. And at least this one of the theories that actually the chondrites created by the collapse of the pre-solar cloud and possibly cleared by the explosion of the supernova nearby. And that happened exactly 4,565 million years ago. And the reason that we know how exactly that happened is that by looking at some of the different chronometers, which are based on some of the isotopes from different materials found in the chondrules, you can see here that actually the dating is very, very exact, and the dating from the chondrules and then eventually to the chondrites only happened in a few billion years. So 4,565 million years ago, the sun ignited really and caused these little chondrules, and the chondrules joined together and formed the planets, and the whole system, the whole thing happened extremely fast in terms of time, because it's only about 5 million years before the planets were actually formed. And this diagram shows a little bit of this is the cloud eventually being hit by the solar wind, and eventually the dust melted and it made these tiny little chondrules. So actually that the solar nebula dust eventually heated up by the ignition of the sun. When the sun ignited, it heated up and it formed these tiny little spears, which are in a sense the fossils of the ignition of the sun. And then stony iron are basically, they're very, very rare, about 0.6% of the finds, which are made of pallasites, 0.4%, and these are pretty much formed by olivine crystals embedded in the iron-nickel matrix. And you can see here the picture of one of them is very, very beautiful. And actually, olivine is actually it's a gem on Earth. People buy stuff made of olivine, and you can actually make gems out of these pallasites. And then mesosiderite are considered kind of like a garbage dump of different meteorites, which kind of crashed into each other and melted, and eventually made the Mesosiderite, which is really a collection of many, many different types of meteorites, all kind of ground up and made fall down to Earth. And in Chile, we have some of the largest Mesosiderite called Vaca Muerta. This is actually a picture of Vaca Muerta. And this one here is also Chilean, from a place called Imilac. And then finally, the iron meteorites, 2.3%. They contain two iron-nickel alloys, which are called kamacite and tannin, which give rise to the Whitman's tidal pattern. We can see this pattern here after you're treated with a very low solution of nitric acid for a few minutes after you polish the meteorite. And the interesting thing about this pattern, that it takes a long, long time to form, and it might take a billion years cooling under the right conditions to actually make this pattern. So they're not possible to recreate on Earth because of the time it takes to form. Here we go a little bit about how to recognize a meteorite. Mostly all the meteorites contain iron-nickel metal, which is detectable by common magnet. Not all of them. Also, the many meteorites that are fresh contain what we call the fusion crust, which is caused by the air friction during the atmospheric entry. You can see here there are two examples of a fusion crust. Sometimes glossy, sometimes look like a burnt bread. There are different types. Also, the density of meteorites is a little denser than normal terrestrial rocks. At least the most common chondrites are about 3.5 grams per square centimeter. Also, all of them, if they contain nickel, iron nickel, and nickel is actually detectable with a very simple color, I call the test called dimethylglyoxine. And also, a lot of meteorites can be recognized because when you found them, they looked like it was made of plasticine, and somebody just pushed their fingers into the material. So you can see a couple of samples here. And also very few meteorites are they're called oriented. So they actually caused by their friction to a ballistic atmospheric entry in a straight line. So let me go back one more here. This pattern here, the remnant ellipse, are very much made by the meteorite just rolling around while it's falling down to Earth, and it kind of selectively not actually burning down parts of it, and that's where the shape. But the next one, you can see a beautiful shape like a bullet. So this one entered the Earth in a straight line, and you can see here what is called melted flow lines on the leading edge, and also in the backside you get some kind of lipping. This lip, which is called the rollover lip, and it's made by some kind of a low pressure turbulence in the backside of this meteorite, when it was going at a very high speed during the atmosphere. And this actually, I will explain a little bit where to find them and where the meteorites have been found, at least so far. They're mostly found in dry deserts, and they're mostly all places that can be preserved for 100,000 years until they're found, like the Antarctica, about 40,000, Sahara, 11,000, Oman in Africa, in the US, roughly about 1,870. In Chile, right now, we have about 2,050, and then Australia, 700. Mostly all the meteorites we found in Chile, actually, they've been laying in the desert for at least 100,000 to 1,000,000 years. I will divert a little bit here. I'm going to show some of the sites in Chile, some of the nice sites. One is the Monturaqui Crater, which is about it's about 1,000. Well, the crater itself is about 360 meters. And basically about 700,000 years ago, there was a 50-meter, most likely metallic iron meteorite that hit the Earth about 70,000 kilometers per hour. And the meteorite completely volatilized. And but you can find this nearby, you find this impactite, which really contain melted ground material with very small particles of metal. This is actually another site, not that far away from Monturaqui, which is called Imilac. And about a total mass of over a ton has been found. And this actually shows basically the metal and olivine crystals. This is actually from Imilac. And this actually goes through what I call the fun part of the presentation, which really shows some of my experience in the desert. I already have been 13 expeditions to the Atacama Desert since 2002, 6 of them to Vaca Muerta, which is the Mesosiderite site. And I found many, many small pieces of Mesosiderite there. I made 2 expeditions to what I found this looked like an impact crater in the desert. And actually, even though it wasn't an impact crater, I found a nice meteorite nearby, which called the Aguada de Varas, my first find. And then 5 expeditions to the dense collection areas in 2009 and 2000 through 2020. And I found about 125 different meteorites. All of them are ordinary, or not all of them chondrites, including carbonaceous chondrites, except one Mesosiderite, of which 61 have been classified and published in the Meteoritic Bulletin database. And then I will just show finally a little bit of the new Atacama tektites, which are called Atacamaites. This is the first expedition we made in 2002 to a place called Vaca Muerta, which is a Mesosiderite and it has a total mass of about 6 tons. And this, I call it it's an area that's been dispersed. It's about 12 kilometers long, about a couple of kilometers wide. It's called the dispersion ellipse. And you can see the small pieces. So this one came from the north, from the southeast to the northwest, and you can see the small pieces fell down first, and some of the large masses fell at the end. And that's because the air will slow down the small pieces earlier than the large pieces. And this shows some of my friends here, Rodrigo, Jan, and Veronica. Rodrigo is actually a very famous meteorite hunter in Chile. And that's me in one of the small pits of the large meteorites. And actually, Vaca Muerta, being a Mesosiderite, it contains a large variety of different materials, which are, because pretty much is a garbage collection of material, most likely from different asteroids. So and you can see it has eucrites, so they have these different colored crystals from white to red. There's some beautiful olivine crystal inclusions, which are almost transparent. This is what I call the normal Vaca Muerta, which contains olivines, metal, the matrix, silicon matrix, and also you find these metallic nodules, which are made of pure iron nickel. And that's where Vaca Muerta is. This actually was a kind of exciting expedition that we made in 2007 while looking for, actually I was looking for a place to go look for fossils in the desert. I discovered, well, not discovered, but I found this crater in Google Earth, which is in the middle of nowhere. It's about 100 kilometers from the highway, and there's no road to get there, nothing, just a place in the middle of nowhere. So we made an expedition with Rodrigo Martinez, and we actually ended up camping right next to the crater. And the crater looked pretty weird when we got there, and we looked for meteorites, and we didn't find anything at all. So it was just it wasn't a meteorite crater. It was actually most likely a collapse, like a sinkhole collapse on the ground. That was very pretty anyway. And nearby, I found this meteorite, which eventually turned out to be it was a real meteorite, and it's been classified as Aguada 001, which is the ordinary chondrite, which is about a little over half a kilo. So that's my first meteorite. And then since 2009, we started searching meteorites, and we got at least many groups, including me and some of my friends and some groups from France and Chile. They started finding so many meteorites, actually they decided to do something called the dense collection areas, and they divided the whole desert in these 50 by 50 kilometer quadricles. And I show in green here the areas I've been searching, called the Paposo, Catalina, Los Vientos, and Aguada de Varas. And actually, roughly about 2,000 new meteorites have been discovered in Chile since 2008. So we went from roughly 50 meteorites in 2008 to 2050. So that's a pretty large increase. And I was just lucky to be in the right place at the right time with the right people to be there. Well, this is actually one of my tiniest finds, which wasn't that impressive. So here, so it's about, this is actually a 1 centimeter cube, and that's the meteorite right here, which turned out to be a pretty rare, actually was the first CR2 found in the Americas. And it's only 5 grams, so it's just a tiny little piece. And interesting enough, turned out to be a carbonaceous chondrite type CR2. And actually, this is a write-up from the periodic bulletin. And the I started reading more and more about the CR2 types meteorites, and they have very large amount of genetic of amino acids, and actually the amino acids actually the same type used by our genetic code of life. And I show here couple of meteorites found in Antarctica of the same type, and it shows all the different amino acids and the proportion found in some of them. And interesting enough, the amino acids have the D, which is the right side, and the L, which is the left side. And actually, that's called chirality. And actually, the life on Earth shows the L type, even though in meteorites they seem to be about the same. So somehow, when life started on Earth, started using these amino acids, they decided to use only the left type, mirror type of amino acids. So that's, to me, this really is a pretty good indication that the solar system was already full of the materials needed to start life. And this actually, you find this material on meteorites, actually they were there at the beginning of the solar system, so they're very ancient. There's another one called CATALINA 001, which is the ordinary chondrite type L 3.4. We found this with Erik Christensen, and you can see here in the picture this is a very pretty type 3, which means that they're very primitive, and you can see the incredible amount of small chondrules in them, and these are materials actually that is the most primitive material you can find on the solar system. This one is Lofientos 028, meteorite we found in 2012 with my son, and that's me, and there's a 12-kilo meteorite, and I will show this in a little while when we finish. And this particular meteorite has a bunch of chondrules, which are the different types. You can see here the barred olivine chondrules, which is these little bars made of pure olivine. You see one made of pure olivine. And this is granular, which has like a bunch of little like sand. Radiopyroxene, which is another type of chondrules. You can see each chondrule is really a small little planet made of different materials. This Lofientos 056, another chondrite types 3 and 5. So it means that the 3 means is more primitive and 5 less primitive. And you can see here in this photo that is made of 2 different lithographies, so different type of material. So this apparently was it's called a brecciated meteorite, which is really made of 2 different types. And that's my son when the day we discovered it. And then the last part of our presentation will be talking about the new Atacama tektites, which they were discovered in 2012 by me and my son Michael. And these tektites were formed when a large meteorite impact produced a vaporized cloud, which solidifies and falls and creating these aerodynamic shapes. And when the scientists studied this, they actually most likely say that it was actually occurred about 7 million years ago by a pure metal meteorite, the iron nickel meteorite. And the discovery was published in 2014, and it's in the Meteorite Society annual meeting in Casablanca in 2014. And this diagram shows here that after the meteorite hit the Earth, it vaporizes, and eventually these little droplets start solidifying. And depending on the distance they fly, it makes these And this shows basically what happened during the impact. It's a very, very large impact. And when I discovered this, I didn't realize where they were, and I sent some samples to the scientists that are doing my meteorite analysis. And they told me two things. One of them, don't tell anybody until they study them and published the study, and also send them the exact coordinates where they found them. So I sent them the coordinates and the samples and stayed quiet for a few years until they did the study. And actually, in the last couple of weeks, they published the final study on the Atacama tektites. It's been published in September 1st in a very influential magazine. And this shows some of the expeditions that were made by the Sergei, the people actually that did they study my Atacamaites. In 2014, they came in very large groups of people and they kind of combed the desert. And they found many, many, many samples for study. And this shows some of the ones they found. This picture here shows the one I found a year later. And this actually shows some of my Atacama tektites, which I found during my few times I've been there to search for them. And you can see the many different shapes like droplets and little spheres and kind of very strange shapes. And here I have some of them look like a little bomb. You can see this one here looks like a little bar with a tiny little droplet attached to it. This one here looks like I don't know, it's kind of weird. So that's basically the Atacama tektites are really produced by very large impact, vaporizing these little droplets and eventually kind of getting stuck to each other and make these shapes. And this is actually the most fun part of going to the desert. Is actually camping the Atacama desert, which is basically it makes you feel like you are in an alien planet because you can be there and don't see anybody. Well, you for weeks without, and the only thing you can see is airplanes fly high in the sky and nothing else. And also the night sky is the most beautiful you can ever see there. It's just never a cloud. It's always beautiful. And that's my presentation for today.
Thank you so much, Michael. That was very informational and awesome to see those pictures of what you've discovered. We have a lot of questions in our YouTube chat for you, so we're going to get to all of those. That's super exciting. I did want to mention from your previous slide of the Atacamaites,
Yes.
those little, very smooth rocks, they definitely remind me of here in Hawaii, we have a similar occurring rock called Pele's Tears. And so, of course, named after the volcano goddess here in Hawaii, Pele. And they're made in a similar fashion, right? I think we talked about this a little bit before, where so these Atacamaites that you're talking about were made from the extreme heat of the impact and then like the material blasting off. But of course, here in Hawaii, we have a volcano where sometimes those Pele tears are made just from like the shooting off of lava and magma itself. But I guess could also come from impacts as well. So it's a really cool similarity.
Yeah, initially when I found them, I thought they were actually volcanic because they do have volcanic shapes and they were made of pure glass, like obsidian, which I think Pele's tears are kind of pure obsidian, correct? They're black and pure glass, yeah.
Yeah, that's right.
Yeah. But the scientists, when they analyzed it, they found right away it was actually impact. Even though the very large impact, which covers a really large area, the scientists had not discovered the source crater. It's actually one of the missing clues of the whole kind of detective story about the Atacamaites.
Ooh, that's interesting. Very mysterious.
Yeah. So how you can find this all over the place, and there's no source crater.
Hmm.
Yeah.
All right. Well, Jamaica, would
Yeah.
you like to read the questions from our YouTube chat for us, or would you like me to? With either one.
Yep.
I can
I'm
do it.
happy to read our questions here from our YouTube audience. Thank you to everyone in the YouTube chat. And let's start off with Michael Mosby. Michael Mosby says, aloha from Memphis, and he has several questions. The first question is, do asteroids, comets, and meteorites contain rare natural resources?
Well, the answer is actually, I didn't show in my presentation that especially the ordinary chondrite, which are the most common ones, have almost exactly the same proportion of elements as the Earth as a whole. So they are, because the Earth was actually made out of this material, so it's nothing that exotic or rare about them. So that's the answer.
Okay, right. So anything that's here would also potentially be made up, have the same components there.
Yeah.
Ah, okay, excellent. And that leads into the next question from Michael Mosby. Do the impacts affect the environment around the impact area more than the craters that they create?
Yes, the answer is actually, we're very lucky we haven't had any large impacts for, well, except for the small one in Russia in the early 1900s called the Sunzuska or something impact. But typically the crater is only it's about 20 times larger than the impactor. So let's say a 100 meter might make a 2 kilometer crater, but it will vaporize material, will send stuff many kilometers away. I say maybe 100 times more. I believe hundreds of miles of devastation. So the crater is actually a very small piece of the impact.
That's wow. And you know, just looking at your images that you were sharing, your pictures, you can really see that in the background. Those, it's just an amazing size from something that's much smaller.
Yeah.
And that leads well into his next point, his next question, which is, he was surprised about the increase in meteorite concentration in Chile. Did you have any clues as to why that increase happened?
Yes. One of the reasons is that the surface in the north of Chile has not been altered geologically for about 20 million years. So the ground has been very stable geologically for about 20 million years. So that allows the collection of material for a long, long time. So I think the only thing that really destroys meteorites in time is the wind, like particles hitting the wind and hitting meteorites and destroying them through basically the wind slowly eroding them. But in the Atacama, they actually dated some meteorites to, I think, about 2 million years old. So they've been laying in the ground for 2 million years.
That is incredible. 2 million years that they've been in there until you came along and your team.
Yeah. So basically, it just represents the normal infall of meteorites on any place on Earth. It's nothing special about it, except this area has been blessed by basically being very stable geologically.
Amazing. Okay, so then a few other questions, and maybe these are to clarify a few things and misconceptions that could be out there in the public. And these are certainly questions that I have gotten before, Michael. So here's the first one. Can you explain the difference between meteors, meteoroids, and meteorites?
That's a trick question. The meteor, I think, is really the more like a falling shooting star, which is a meteoroid may be something that produces a shooting star, maybe before the shooting star, and then meteorite is really what is left over and falls in the ground. And typically when a shooting star goes through the atmosphere, they normally just get vaporized and become dust. And they only, well, eventually will fall down to Earth as dust. So you can, but a very large part of the meteorites or shooting stars actually vaporize. Only very small part of is left over, except when they're very big and made of iron, which they already vaporize too much during the entry.
Thank you for that clarification. Okay, so next, what is the difference between comets and asteroids?
Well, comets are, as I showed in one of the diagrams, they're made mostly of ice and rocks, and so they're more like made of volatile material. And then the meteorites and asteroids are made mostly of more rocky material without any stuff that can actually, no water or seal or no volatiles.
Okay, thank you for that distinction. No volatiles, no gas, nothing that's going to outgas is going to be found there. Okay.
Yeah, because the main thing about comets actually they're outgassing, and you can see the tails, which is really. And so they were made in a different section of the solar system, which allowed the volatiles to stick together, like water and CO2, whatever the material made of mostly all the outer planets. So the comets are more related to the outer planets, but and then the asteroids are made of the inner rocks.
Thank you so much for answering our questions. And those of you in our YouTube audience, if you have more questions or comments, please feel free to drop those in the chat. We have about 9 minutes left, and I believe Michael has some awesome things to share with us.
Yeah, I'm going to show you some of my meteorites. I don't know you guys. I will show you it's kind of heavy. These are little babies. It's about 12 kilos. It's called Los 128. And it's my biggest meteorite. And then I have this one here is about 4 kilos, which actually is a nice sample because it contains fairly nice remnant. So you see this kind of indentations, or we kind of show how they've been eaten up by when they're falling down in the atmosphere. They have this kind of weird shape. So this thing was actually came in by rolling, and it was selectively being the surface was being eaten away by the atmosphere coming in. And then here, so heavy. This one represents a very nice, it's a 6 kilogram oriented meteorite, which I have not classified yet. And it was found by my cousin Miguel Munoz. And you see it has the shape of a turtle. So this one came almost straight down, and you can see this kind of these little riblets of molten material, and it was entering the atmosphere. Yeah, so it's very pretty, oriented, kind of heavy. And then here I'm going to show you some of my Atacamaites. These are Atacama tektites, which are really tiny, but very pretty. I'll show you a couple more. This one here shows another Atacamaites. There are many of them. See, one here looks like a little tree. Oh, sorry. This one shows a little tree here with the droplets. Oh, this one here has a nice droplet. See, one here sees the little droplets. That it looks like a drop, but then it has another droplet attached to it. And see what else I have here. This interesting meteorite. We have, let me see if I show you here. Has this very dark line, and this actually called an impact line. So this was very likely hit something else and melted in space before it fell down to Earth. And let's see. Here you have this actually is a piece of a Mesosiderite that we discovered with Eric Christensen. This is a pretty rare find anyway, and you can see a lot of metal. And that's one of the things you can recognize a meteorite, because all we have is lots of pure metal, which is really shiny, which is not found on any material, natural material on Earth. And then finally, I'm going to show you a couple of little samples. This one here is a tiny little sample from Mars. It's a really tiny one. I bought this I think I bought this in eBay. And then this is a piece of the moon, really tiny. This is about 0.3, 0.4 grams. And actually, I got this by swapping, I think, about 50 tektites for this. And let me show you one more, which is the tiny little CR2, which is the one that represents the amino acids. So this is really tiny. So even though it's very, very small, it has a pretty important scientific value. And that's about it. I think I have all my.
That is absolutely amazing, especially the one that looks super metallic.
Yep.
If someone wants to get into finding meteorites, what would you suggest they start with doing?
Well, in the Atacama Desert, all you need is a good eyesight, a good truck, a good four-wheel drive truck, lots of water, because you go into a really very dangerous territory, extremely high temperatures, no way to communicate to the outside world, no cell phone, nothing, just going. And so basically water, a good car, and good eyesight, because we usually just drive in these flat areas and look for any weird looking rocks. Actually, there are areas that have no rocks at all. And whatever rocks you found, you check it with a magnet. And if it's magnetic, very likely it's so usually you have a magnetic. I don't have a sample here. It's a stick. It's a piece of plastic with a metal or a magnet in the end.
Oh, that's pretty amazing. Okay, that seems very doable outside of not being in the Atacama Desert. But if I were, it seems like a very doable thing to get into.
Yeah, I do have a metal detector, but I have never used it. I have a really beautiful metal detector. I actually used it once because I found 3 meteorites right next to each other, and there was like a puzzle, and it was missing a large piece. So I used my metal detector to find the lost piece underground.
That's amazing. I've always wanted to use a metal detector. Now I have a good reason to do so. Thank you so much, Michael Warner. And thank you everyone in our YouTube audience for joining us today. Back to Leilani.
Well, we have about 2 minutes left of the show. So if you have any last comments or questions, please leave them in the chat. I have just one last question for you, Michael. How long does an expedition take when you go out into the desert to look for meteorites? Is it a day trip? Is it a whole weekend? Is it a week?
Well, typically we go for 4 or 5 days. Actually, from La Serena, we can leave early in the morning and be there at the site before sunset. So we can find at least 1 or 2 meteorites before sunset. And then the next day we typically go for 4 or 5 days, and we go from tektites. Actually, you just go to areas that the most productive areas are areas that have never been touched or driven by anybody before. You find the car tracks that you know you're in the wrong place.
I see.
Interesting enough, the car tracks stayed in the desert for like 20, 30 years. I see my tracks I left 20 years ago, which is it's kind of sad because basically you leave in your footprints also. Footprints actually, it's like the moon. The footprints stay there forever. You see, and that's the reason they're so stable. The surface is so stable that anything you do, you're probably altering.
Well, it sounds like a very interesting environment to be in, and how appropriate for it to be like the moon or like another planet, and you are finding pieces of other
Yeah.
objects out there.
Yeah. In the beginning, we were so productive that I think one time we found, I think, 50 or 60 different meteorites in a single day.
Wow.
It was, yeah, it's before anybody else was. Right now, there's a lot of people, a lot of groups coming. I know people actually they made paid tours so they can bring people to look for meteorites for a price. I can guarantee you to find a meteorite any day. But
well, it sounds very interesting. Well, that brings us just about to the end of our show. Thank you, everyone, for joining us. Thank you, Michael, for being here. Happy Asteroid Day. And I'll see you all again next week for another Live from NOIRLab.
Sakura Nani, take care.
Take care.
Bye, Danica. Good night.
Aloha.
Aloha.